Hello everyone and welcome to the next webinar series. This is Aparna Deshmukh, Technical Director with Next, and I will be your moderator for today's session. We are eager to learn all about our today's webinar titled Guidelines for Using FRP Dowels in Concrete Pavement. A PDF of this presentation can be found in the handout box. You can use the PDF to follow the presentation and take notes if you desire. You may use the question box to ask questions during the webinar, and a speaker will be happy to address them at the end of the presentation. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 1 PDH. Your certificate will be available in ACI University under the Certificates tab within 2 days. For those who cannot join us live, the on-demand recording will be made available about a week after the live presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for one learning unit. Please take note of a disclaimer on the screen for the next webinar series. So let's get started with a short description of our today's webinar. It will cover the latest development in FRP Dowels, focusing on the physical and mechanical requirements for their effective use in load transfer systems. It also highlights design strategies for achieving pavement performance comparable to solid metal dowels and presents real-world project results alongside updated specifications. Our learning objective for this webinar are as shown on the screen. Let's welcome and introduce our today's speaker, Dr. Mark Snyder. So Dr. Mark Snyder is the president of Pavement Engineering and Research Consultants, LLC. He has over 40 years of experience in concrete pavement engineering and 13 years of teaching and research in civil engineering. He is known internationally for his expertise in dowel load transfer systems. His work includes developing dowel design procedures, full-scale testing, and creating AASHTO style specifications. He also provides technical support to paving contractors, DOTs, and dowel bar manufacturers. So Mark, welcome to the next webinar series. We also have Dr. Peter Taylor, who is the professor and director of National Concrete Pavement Technology Center, Iowa State University. He is also with us today, and he will be there for question answer session. So Mark, let's listen to your presentation.
The outline, a little introduction for background and context. We'll talk about physical and mechanical properties of FRP dowels, fiber reinforced polymer or plastic dowels, the important ones that we think that affect performance of concrete pavements and behavior of the dowels in the system. We'll talk briefly about load transfer system design using FRP dowels. Talk a little bit about construction experience that's been accrued on projects with FRP dowels. We'll summarize performance to date of pavements constructed with FRP dowels, provide a little bit of the agency and contractor perspectives, and then wrap things all up at the end with a couple of recommendations and conclusions. So by way of an introduction, I would say that FRP dowels for concrete pavement are not yet widely approved, but they are very rapidly gaining acceptance. A review of the literature that I could find revealed only Idaho, Iowa, and Quebec as being states and provinces that currently have specifications, standard specifications on the books for using FRP dowels. Belgium also has standard specifications as well, so another country. But there have been a lot of projects built, and there are a lot of states and agencies that have special provisions and have constructed demonstration and research projects. So I suspect that those folks are moving rapidly towards incorporating them into their standard specifications as well. The key drivers, I think, for the rapid acceptance and move to adopt are the lightweight ease of handling of these dowels, the fact that they are non-corroding. It's not like you've got a barrier where you're trying to protect something, you've made something corrosion resistant. FRP simply is not corrodable, it's non-corroding, right? A driver working the opposite direction, prohibiting adoption, is the fact that FRP elastic modulus, the stiffness of the material is far less than that of steel. So it's a different product, a different material, going to behave differently in the field. And there's questions about, well, how's that going to work in the long term? We're getting to the point where we're starting to have some long-term performance. There have been a number of successful trials and demonstration projects built since about 1983, and that has led to the development of the specifications that you see above. In fact, all those specs that I mentioned above, Idaho, Iowa, Quebec, Belgium, those are all within the last 5 years or so that they've developed standard specifications. So we're seeing movement in that direction. So in this presentation, we're going to talk about a little bit of guidance for using FRP dowels in concrete pavements as alternative to conventional epoxy-coated steel dowels, based on my review of research and case studies from, and also from interviews with agencies and contractors. So there are a lot of different factors that affect the durability and behavior of FRP dowel bars, and therefore their general suitability for use in concrete paving applications. And those include the materials themselves, the components, the resin types, the fiber types, the amount of the relative proportions of those two, the fiber content and the resin content, the way that they are manufactured, the degree of curing and the smoothness of the bars on the outside surfaces. And then I think the one that we all tend to think about first, the mechanical properties, particularly the strength and elasticity. Abrasion resistance probably doesn't come up in your thoughts right away, but if you think about having a softer material out there and it's sliding back and forth in a joint for, daily cycles for years and years, you may have some potential for abrasion there. Moisture absorption comes into play as well. And there are some other less important factors, but we're going to talk about these here because they are probably the most important ones that come up in conversation over tea most often. First is the resin type, and the type of resin that is used affects the strength of the FRP and the durability through the quality of the bond that the resin has with the fibers that are used. Now, there is a brand new specification by ASTM out for the use of FRP dowels in concrete pavements. That's ASTM D8444. I think it was approved back in May of this year, and it has just recently appeared, I believe, in print within the last month or so. And where that spec applies to resin type, it does permit only vinyl ester and epoxy thermoset resins. And it specifically says no polyester. Base resin can't have any polyester in it. Now, none of the other specs I talked about previously, any of the state specs or provincial specs or whatever, none of them have this language in them. But effectively, they've kind of all gotten there through a performance-based approach. They limit moisture absorption and glass transition temperature. And as we will see in a little bit, those requirements effectively preclude the use of polyester resins in FRP paving dowels. The fiber type, that is what provides your primary control over the tensile strength and elasticity of the product. We see only at this point, we see only glass fiber in paving application dowels. I know that there are carbon fiber and basalt fiber products being used in rebar occasionally. And I've seen basalt proposed for use in paving dowel, but I'm not aware that it's been brought to market. So all we got right now is glass fiber dowels. And the E-CR fiber is the one that is the preferred fiber. It is boron free, which apparently is something that makes it more resistant to alkaline attack. But it is that resistance to alkaline attack that is the key factor here, because obviously concrete provides a highly alkaline environment, very high pH levels in the pore water of concrete. So that's a very important factor. As far as the proportions go, the more fiber you use, the higher strength you get, the higher modulus elasticity you get. But we need to have enough resin there to fabricate a nice smooth bar. So typically what we see is a minimum requirement of 70% fiber, and we don't very often see more than about 80% fiber by weight in FRP dowels. Glass transition temperature, ASTM standard test D3418, and there are a few other ones as well. This is defined as a temperature where the polymer behavior changes from being a stiff, or rigid, glassy material to a viscous or rubbery material, as you see in the graph on the right-hand side here. There's the T sub G designated by the arrow there. And that is an indicator of a couple of things. It's an indicator of the resin composition. Because if you look down at the bottom here, we see that the vinyl ester resins that are typically approved have a glass transition temperature greater than 240 degrees Fahrenheit. Polyester resins are typically less than 195, which is why you see the specifications require typically a glass transition temperature in excess of 212 or 230. Basically a number that's going to preclude you from using polyester. Okay. Moisture absorption is another mechanical property that we're concerned with. Increased absorption of moisture into the dowel bars or into the resin is associated with reduced durability of that product. And if you look down at the bottom again, typical values: vinyl ester less than 0.1%, polyester greater than 1.25%. So clearly, if we control our moisture content, we're also going to control the material that's being used here. And the specs that are out there now typically specify long-term saturated values, and that would be like 7 days or longer of saturation of less than 1% for product qualification. 24-hour values, a shorter test makes it more useful for quality control testing, and that's usually limited to less than 0.25%. So again, both those values are going to eliminate the use of polyester resins. Get into the mechanical properties, the transverse shear test, and this is an ASTM standard test as well. You see the test jig over on the right-hand side there, and there's actually a rebar in that jig right now. And what happens is that that rectangular block that you see in the middle is pressed down through the rebar there, or in our case, the dowel bar. And the force required to push that through, creating a double shear plane on each side of the block, that is the stress that is specified for the product, okay? And current specs for FRP dowels typically require, depending on whose spec you're looking at, between 19,000 and 23,200 PSI. ASTM D844 requires that higher number. I want to point out this is really not a critical test for performance in the field, because typical shear loads in a dowel bar and a pavement are less than 3,000 pounds. A lot of times they're less than 2,000 pounds, particularly for the larger bars there. And if you look at the stresses that result, you're going to be looking probably at less than 5,000 PSI. So we're way below these limits. It's not really important from a behavioral standpoint in the field. It's just for the quality of the bar. Here's one that's a little more relevant, perhaps, the horizontal shear strength, or the flexural strength, if you will, of the bar. And here's the test rig. Typical requirement is 7,300 PSI flexural strength. And again, we don't use this in design, but it is useful in the specifications for comparing the quality of different kinds of products. The bond strength test, or what we would call the pull-out test. And this is not an FRP bar on the right here, but this is an example of what it looks like. You have a dowel bar which is embedded into a specimen of concrete, and then that entire specimen is taken, and a grip is applied to the dowel bar, and it is pulled from the concrete, and you measure the force required to pull that bar from the concrete after it's been properly anchored, okay? And there are a couple of standards. AASHTO or ACPA have both developed test methods with the same designation, T253, Section 6, and ASTM D844 has the same, a very similar procedure outline. They're all pretty similar. Typical specification limits are around 3,000 pounds. Now the ASTM spec and some of the agency specs, they limit their bond strength rather than pull-out force. So what they're looking at is the force divided by the area of the exposed surface of the dowel bar that's embedded in the concrete. And if you do the math on the specifications, so they end up with different stress values for different size bars, which seems kind of counterintuitive maybe a little bit. But if you do the math on all of them, the force works out to around 3,000 pounds for the different bar sizes. So everyone's kind of coming in around this 3,000 pound limit ballpark, okay? In order to meet that spec, it may be necessary to use a debonding agent or a lubricant. We typically require that for all our seal bars. Some FRP bar manufacturers will state that they don't require that. They don't need it for theirs, that they can meet the pull-out force without it. In the words of Ronald Reagan concerning the Russians, I would say trust but verify. I would check, okay? Because we have seen occasions when they did not meet that specification requirement, where there's some significant bonding taking place. And I'll talk about that a little later under the construction part. Abrasion resistance is one that we don't really see in the specifications except for the ACPA T253 test. Long-term abrasion of FRP dowels has been noted on at least one old study from 1987 in Ohio. And again, we'll talk about this later on. It did result in significant loss of section of the dowel at the joint. Hasn't been documented in any other studies that I'm aware of, but maybe other folks haven't been pulling the dowel bars out to examine them after years of service. I'm not sure what the reason is. So it seems to raise enough of a cautionary flag that it may be a test that's worth doing. And if you look in the lower left-hand corner, this is the AASHTO T253 abrasion resistance test. The bars are mounted horizontally. You've got a concrete block with a specified mass, and you've got this mechanical rig that's just moving that block back and forth 10,000 double strokes. And you measure the loss of cover. And this test was developed for epoxy-coated bars. It's really about measuring the resistance of epoxy to abrasion. But certainly it can also be used for FRP dowels as well to note whether or not they have any abrasion resistance problems as well. The photo on the right comes from the University of Pittsburgh. Dr. Vandenbush there provided this. They have developed an apparatus, and they have a second one on loan from American Engineering Testing up in St. Paul, Minnesota. They're doing a lot of abrasion testing there on different products. So it's not currently specified by anybody for FRP bars except for the ACPA test, and therefore we really don't know what the practical limits should be for this particular test. You'd need to establish those limits based on how much section loss would result in either a reduction in stiffness that's unacceptable, or enough looseness around the bar at where it comes out of the concrete that you'd have lower load transfer efficiency values. And I don't know what those numbers are. But certainly even running the test without a limit would give indications of the relative abrasion resistance of different kinds of products. So therefore, I think it's probably something good to include and probably ought to be in tests going forward. And we need to do some research to figure out what those limit numbers are. Load deflection. Here's the one that everyone comes to first when you think about FRP bars. How's this thing going to behave once we get it out there in the field relative to steel, given that it is so much more flexible because of the inherent material properties? Well, there's a few tests that are out there. AASHTO T253, AASHTO T253 has a test where you have blocks of concrete, typically around 10 inches thick, 1 foot deep into the page here, 1 foot wide specimens, and the end blocks are anchored to a rigid foundation. The center block is unsupported, and you have one bar going across each joint. You apply a 4,000 pound uniform load across that center section there, and then you monitor the relative deflection of the center block relative to the end blocks, and you measure that across each of these two joints on both sides. The specification in AASHTO, and again, this was developed for epoxy-coated steel bars, limits that deflection to 10 1/1000ths of an inch, or 1/100th of an inch. The new ACPA T253 test, which was developed specifically for use with things like FRP dowels and hollow dowels and plate dowels and everything else that's not a standard cylindrical dowel, says we want to look at the entire behavior of the dowel grouping. So we got a 4 foot wide specimen. Still, the end sections are supported. The center section is unsupported, but we're using a plate load, a concentrated plate load, 12-inch diameter plate, just like an FWD plate. And we place that directly over the edge of a joint, just like you would see in the field if a wheel load passed over the joint. And we measure the relative deflection again across that joint. And the test has been kind of calibrated experimentally such that the load that's applied, 10,700 pounds, gives you the same behavior for this test that a single dowel does in the AASHTO T253 test with a 4,000 pound load. So it's intended to be equivalent. If you ran the 1.25 inch epoxy coated dowels in this, you should get the same results as you would in the AASHTO test. So we limited the relative deflection to 10 mils here as well. These are static load tests, and they tell you, what the dowel is going to behave like when it's first installed. But if we want to know what it's going to behave like in the long term, we want to have a dynamic test, and we want to load it many, many, many times. So Pennsylvania has developed or adopted, I should say, a Pennsylvania test method number 642, which uses large-scale specimens. And you can see here they've got 3 bars, again, simulating a wheel path. And then the load is placed right at the edge of the specimen. And you can see 2 actuators here. And these actuators are applying the load sequentially, first on the left, then on the right, to simulate the passage of a moving vehicle across that joint. And they do that 10 million times. And they've established limits on relative deflection after 1 million cycles. And then again, how much more happens between 1 million and 10 million, what the additional increment is. And this is, again, a photograph of testing equipment in the University of Pittsburgh, provided courtesy of Dr. Vandenbush there. So we've talked about a lot of physical and mechanical properties. There are, as I said, this is a photo of the new ASTM D8444 standard spec. Covers a lot of this stuff. On the material properties, the tests are described in the ACPA test method. You can find that on the ACPA website, acpa.org, and drill down to their specifications and guidance documents there, and you can find these there. And I would note that these documents are currently under consideration by AASHTO as possible replacement for the AASHTO T253 and M254 tests. I think it's being balloted next month. Okay, so that's kind of a brief summary of the mechanical properties. Let's look at the load transfer system design. And if we look at concrete pavement behavior, probably the 2 things that are the most disconcerting failures that we have are joint faulting, or step off across the joints, where you get that ka-thunk, ka-thunk, ka-thunk as you drive down the road, and then slab cracking. Nobody likes to see slab cracks. And one of the things that's very important to both of those distresses is the deflection of the pavement, the relative deflection across the joint. Relative deflection being the differential deflection when I load, for example, loading the side on the left, and the side on the right doesn't move down to the same distance that the one on the left did. And what the magnitude of that is, that delta value that you see here, is actually the combination of 4 different components. There is the deflection of the dowel at the joint face, so this point right here that you can see, and you can think of that as being, if the concrete is a very, very, very stiff foundation and the dowel bar is bearing against it, it does compress the concrete slightly, and you get a little bit of deflection at the joint face. It's probably only 1 or 2 thousandths of an inch, but it's there. And in doing that, it establishes a slope of the dowel bar coming out of the joint face. So the second component of our deflection across the joint is the slope times the joint width. The third component of relative deflection is shear deformation. The fact that as we apply a shear load, the material tends to deform. It deforms vertically in response to that shear load. And the softer the material is, the higher that shear deformation is. And finally, the fourth component is the flexure. We're inducing a bending moment into that bar across the joint. And so there's going to be some bending of the bar taking place. And that is a component of the total relative deflection as well. Now, for typical contraction joints, where the joint is very, very narrow, say it's only 1/8 of an inch or 1/4 of an inch at the very most in the dead of winter, the shear deformation component and the flexural the flexural component, I'm sorry, let me back up. The dowel slope becomes very small, and the dowel flexure become very small. Okay, so it really relates back to, in practical cases, that the joint deflection at the embedded face and the deflection due to shear deformation. Those are probably the 2 most important ones. And how do our steel properties and our FRP properties affect those numbers? Well, you look at the elastic modulus of steel, 29 million PSI. Depending upon your composition for your FRP bar, it's going to be maybe only 20 to 25% of that. The steel is 5 times stiffer for the same size bar. Okay. And then that shear modulus that we talked about, it's a factor of 20. The shear modulus of concrete, around 11 million PSI. For FRP, probably down around 500,000. So you can see why, if you have a very wide joint, you get 22 times as much shear deformation across that joint with an FRP bar. Again, fortunately, we're talking typically very, very narrow distances, so the numbers become not terribly important, but it's something we need to be aware of. Those are things that affect the behavior. These are the things that cause us to have different load transfer efficiency, and relative deflection values with the FRP bars. For the elastic modulus, if we reduce the stiffness of the bar, E times I, the section modulus for the same size bars, we're going to have a 20%, 80% lower value for FRP than we do for steel. That means we're going to have higher deflections due to dowel bending. We're going to have increased bearing pressure on the concrete at the joint face. And experimentally, work that was done by Max Porter at Iowa State University indicates that it also appears to reduce the apparent modulus of dowel concrete support, or that K value, the stiffness of the concrete, which again increases the deflections at the joint face by a factor of about 2 or more. Okay, and then the reduced shear modulus, as I said, can cause potential problems as well. So how do we consider this in design? Well, the first thing to remember about dowel load transfer system design is that there are no commonly used load transfer system design procedures available. There aren't. You look at any state specification or state design plates, and it's all, well, if you got a 10-inch thick pavement, use 1.25 bars. It's all kind of evolved to the point where everyone has just reduced things to a table of sorts, a design table. Now, that's not to say we can't look at the effects of different sizes. You have Pavement ME design software, which will provide us with predictions of pavement cracking and faulting and ride quality based on trial designs. And we can put in those in Pavement ME. We can put in the reduced modulus of the FRP bar, and we can change the diameters, and we can change the spacings, and we can see how that's going to affect the predicted behavior of the pavement. But it's not really a design procedure per se. It's a trial and error process. Like I said, steel load transfer system designs have evolved over the last 100 years to a standard, and that standard is we use solid round steel dowels, usually epoxy coated with something to prevent corrosion. Dowel diameter is going to be the slab thickness divided by 8. At least that's what it was until the last 20 or 30 years. Now we started beefing it up a little bit more to decrease bearing stresses. So we add up to 1/4 inch on top of that now, right? So you got a 10-inch thick slab. It's going to be 10 divided by 8 is 1.25 inches. Most states are using 1.25 inches to 1.5 inches bars for a 10-inch slab. Dowel length has been standardized at 18 inches, other than the good folks in Minnesota that use 15, successfully, I might add. And the dowel spacing has been standardized at 12 inches. That's our steel load transfer system design. So what do we do for FRP? What's our design approach for FRP or any non-round steel system, whether it's hollow dowels or plate dowels or whatever you got? Well, one concept is you develop the new system to have properties or behaviors that are comparable to or better than the current standard. One approach that's been recommended by, again, Max Porter at Iowa State University about 26 years ago was to use relative deflection, which is, again, that difference between the loaded side and the unloaded side of the joint. And I agree. I think that's a pretty good indicator of what's going on with the load transfer system, because it's focusing on just across the joint. And the only thing affecting that slippage across the joint, the biggest thing affecting the slippage across the joint, is going to be the dowel bars and maybe any aggregate interlock you got there as well. And we can estimate it analytically. We've got Freeburg's bearing stress analysis, and I'll throw that equation up here in a little bit. We've got finite element analysis programs. We can even measure it experimentally or in practice. We can go out in the field and measure it. We've got a couple of tests. ACPA T253, the multiple dowel load deflection test, tells us what relative deflection is for a particular system on a fully bedded foundation. And the Pennsylvania test method, 642, gives us another indication of relative deflection. The very first load cycle you put on it gives you a relative deflection. I will say right here, load transfer efficiency, or LTE, is not a good indicator of equivalence. Okay, that's the deflection of the unloaded side divided by the deflection of the loaded side. And why is that? Well, very simply, the relative deflection gives you a relatively pure measure of what's going on at the joint. Relative deflection does not, because it takes into account what the deflection of the loaded side of the joint is as the control, okay? Let me give you an example here. Look at this column. It says relative deflection of 2 mils. All these values of load transfer efficiency come from having a relative deflection across a joint of 2 mils. If you have a very stiff foundation, the loaded side deflection is 4 mils. Unloaded side is going to be 2 mils. Relative deflection is 2 mils. Load transfer efficiency is 50%. An awful lot of state specifications and poorly educated people are going to say, oh, 50% load transfer, we have to throw that out. That's no good. But clearly, it's not bad. It's very, very low deflections. That's a pretty good system. Come down here to the other end of the spectrum. Put that same system, that same joint on a very soft foundation, and now the whole pavement deflects a greater amount. The loaded side deflects 20 mils, unloaded side deflects 18 mils. Our relative deflection is still 2, but now it gives you a 90% value. We made the system crappier, and we increased the load transfer efficiency as a result. Okay, load transfer efficiency will lie to you. Relative deflection is what we need to use. We developed this concept of load transfer efficiency back with experiments in the lab where the foundation was controlled, and in the field it doesn't work. We need to expunge load transfer efficiency from all of our specifications and go back to relative deflection. That's the pure measure of what's going on at the joint, the relatively pure measure. Okay. Design approach. So we can also, if we don't want to look at relative deflection, another thing that's been proposed has been to look at bearing stress equivalence, because the relative deflection is a static measure of equivalency, but it doesn't tell you what's going to go on in the long term. And in the long term, if you have very, very high bearing stresses, we believe that we will see some potential for loosening of the dowel bar over time as the concrete deteriorates around the dowel bar. So looking at bearing stress and comparing bearing stresses may give us an indication of long-term behavior. And here's Freeburg's bearing stress equation. I'm not going to go into it and define all these terms here, other than, K is the stiffness of the concrete, P is the transfer load, Z is the width of the joint. And then you got your E and your I, which are your stiffness of your dowel bar. Once upon a time, back in 1956, ACI 325 had a subcommittee that developed a limit on bearing stress based on some studies by Marcus and Henri Marcus and Teller and Cashel and other folks. And this is the equation they came up with. Limited bearing stress to a function of the compressive strength of the concrete and the dowel bar diameter. Okay, those are the things that played in. This kind of disappeared. I think ACI withdrew this, and there really isn't any guidance on what the limiting and bearing stress is now. But even without a limit, we can at least calculate what the value is. And if you have a higher bearing stress value, you know that you're probably potentially more susceptible to long-term development of looseness on the bars. I would note that this original equation was very, very conservative. It had a factor of safety of about 3 in it. The other thing we can do is we can determine equivalence dynamically using the Pennsylvania test method 642. And again, PennDOT's specification limits are relative deflection is limited to 7.5 mils at 1 million load cycles, and then no more than 2.5 mils of additional looseness over the next 10 million cycles. So if we summarize all that stuff up and look at all the research in the literature, which I haven't gone through all of it here, but the bottom line in the literature is researchers have concluded that in order to be, again, equivalent, FRP dowels need to be 20 to 30% larger diameter than round dowels, or you got to reduce the dowel bar spacing from 12 inches to maybe 8 inches or even 6 inches, because that then reduces the amount of load per dowel, and that would then reduce the relative deflection per dowel. Or you do both of the above. Okay, that would be the research recommendations historically. There's been some research done relatively recently in West Virginia by Vigier and company that suggests that FRP dowels don't have to be as long as steel bars. They can be 4 to 6 inches shorter, and that would offset the cost of larger or more closely spaced bars if you went that way. And the reason they can be shorter is because the bar is more flexible. The deflection profile inside the concrete where it's embedded takes place over a shorter distance. And it's generally accepted that once you get past the first point of the second point of contraflexure, anything beyond that is not really doing any good. So since the FRP dowels have a shorter wavelength inside there, that second point of contraflexure is not as far into the concrete. So that's what research suggests. But we need to look at field performance, because our steel dowels have evolved over 100 years of research and field experience. And FRP dowel, until recently, has been mainly based on the design of those dowels, has been based on theoretical equivalence concepts like we've been talking about, because we haven't had much field experience. The oldest project out there is only a little over 40 years old. But we're starting to get some stuff now where we do have these 40-year-old projects, and there are some of the more recently built FRP dowel projects that have longer and longer performance records associated with them. And what we're finding is, well, there is generally lower load transfer efficiency for whatever that's worth, and higher relative deflections with FRP bars, but pavement performance has not been appreciably different. No differences really in ride quality or distresses. So we need to factor that into our considerations for design. And here's an example. Iowa US 65, built in 1987. So this puppy is 37 years old this year. 4 different designs, 1 7/8" bars on 8" spacings and 12" spacings, 1.5" bars on 8" spacings and 12" spacings. And you look at the pictures, there's no faulting, there's no slab cracking, and they're 37 years old. Looks pretty good. And that's kind of representative of what Wisconsin, Route 29, there's a number of older projects that are out there that have performed pretty well. So the conclusion, if we build field performance in, is that matching deflection and bearing stress values of current steel systems and recognizing those current steel systems may be pretty conservative. That's going to result in alternative dowel systems, whether it's FRP again or hollow dowels or anything else, that are unnecessarily expensive and inefficient. And there is evidence that in at least a few cases so far, FRP bars can be substituted for solid steel dowels of the same size and the same spacing with not much apparent impact on long-term performance. We'll talk about field performance more later. So when it comes to design guidance, we got a couple of approaches. A conservative approach, which is, follow the research recommendations. Increase the FRP dowel diameter by 1/4 inch and use the same length and spacing as for solid steel. Or you could take a more aggressive, or you might say informed approach, and use the same dowel diameter as for solid steel. And you could even reduce the dowel length to as little as 11 inches to account for the higher flexibility of the FRP bars. I would still keep the spacing the same at 12 inches, just for standardization of dowel baskets and dowel bar inserters and so forth. Let's talk about pavement construction a little bit. On the pro side, benefits, lightweight. Individual bars only weigh about 30% the weight of steel. And when you put them in a basket, the baskets are going to be 50 to 60% lighter than steel baskets. Contractors like that. Workers like that. Potential for fewer injuries. They can work faster, move faster. There's potential for improved productivity and so forth. They may not, I'm going to put the emphasis on may again, may not require the use of a bond breaking agent. Again, trust but verify there. They are non-corroding. They can be bundled and stored, as you see here, without having gummy protectant materials. If you've ever seen a bundle like this of steel epoxy coated bars with the Tectile coating on them, and they're all gummed up together, and then you try to break those apart to put them into the dowel bar inserter, that's fun. Not. And there's no coating or cladding that might require repair in the field. Although I will say, if I saw a bar, an FRP bar with a big gouge in the side or something, I'd either discard it or I would have a repair process available to fill that gouge in, because you do not want concrete penetrating into that gouge and keying in and locking that bar up so it can't move in the joint. Okay, so potential for field repair is there, but quite honestly, typically we don't see it. Don't see the need, I should say. So it all sounds well and good. It's all unicorns and rainbows, right, so far. But there are potential pitfalls in construction. And one is the potential for high pullout forces if you have an unlubricated bar, which I've talked about already, or a rough surfaced bar. Now, typically our bars here in the States, our manufacturers are doing a pretty good job here. This what they typically look like. These gray bars are FRP bars provided by Master Dowel, as an example. On the left here are some FRP dowel bars, believe it or not, that I took a picture of on a demonstration project in Poland last summer. Okay, this is what they were using in Europe for an FRP. And you can see the texture on that bar. I mean, and quite honestly, you ran your hand across it and you picked up little fibers into your hand, and your hand itched for a day afterwards. Not good. I wouldn't trust that. Even if you lubricated that, I don't know that you'd get proper slippage on that. So we need a good smooth surface. And if you don't have it, then you've got potential for a problem. And it has been suggested, this is why I say trust but verify. There was a job in Washington State on a dowel bar retrofit job where a non-lubricated FRP bar was put in to a dowel bar retrofit project, And the repair material they use, and I'm not sure of what the repair material is, I suspect it was probably a polymer concrete or some proprietary material, not just a regular Portland cement concrete. But they found, the contractor noted that that stuff stuck to the bars really, really well, because they had to excavate a few of them out to replace them, repair them, whatever. And they noted a lot of adhering repair material onto the bars. So again, trust but verify on the lubrication issue. Other construction issues, we need to have reliable attachment to the basket cage assemblies. We don't want bars dropping out all over the place in the field. Here's a number of proprietary systems that are out there. Caps on the ends of the bars that clip onto, the steel basket, a spring steel arrangement that grips the bar. And here's one where they actually drill a hole across the center diameter of the bar, and they slip a steel rod through it and then weld that to the dowel basket. That certainly works. There are also non-metallic basket assemblies, and these are particularly important when you go to placing FRP bars in the area of, for example, tollway gantries and areas with heavy instrumentation in the pavement where you don't want any metal in the pavement structure whatsoever. You need a non-metallic basket. There are options available. And these are often assembled in the field even. They're modular, so you make them as wide as you want or whatever, okay? Another issue of concern, dowel bar float, in quotes, during concrete construction. Well, FRP density is kind of low, 120 to 140 pounds per cubic foot. Concrete is 150, so in theory, yes, there's a little bit of a buoyancy effect there. It's about a half pound per bar by my calculations, roughly. I would note that the density of steel is 490 pounds per cubic foot. There is quite a downward negative float with steel potential. So if we don't see much movement with steel, we shouldn't see much movement with FRP, but there has been upward movement of FRP noted on projects in Idaho and Washington. And I suspect that it might be caused more by upward movement of the concrete in between the vibrators. If you got a vibrator in the concrete and the bar is in between them, and the concrete under the vibrators is kind of consolidating, there may be a little bit of an upward movement in between perhaps, and that lifts the bars perhaps. I don't know what the mechanism is. Bottom line is there is potential for movement of these bars, and that's why a lot of states prohibit the use of FRP bars with dowel bar inserters, and they require baskets. I think our last one here is you can't see them with magnetic locators, okay? If you got an MIT scan device, you cannot see these bars. You got to go to other devices. You got to use ground penetrating radar or ultrasonics like the Mira device, or you can use manual probing techniques to verify the positions of the bars. Okay. Closing in on the end here, performance of concrete pavements using FRP dowels. There's been a lot of research on dowels, FRP doweled concrete pavements. And these are all documented in the report. Here's some of the key conclusions, okay? FRP dowels usually have lower load transfer efficiency values than solid metal bars of the same size, both initially and over time. And they tend to lose their load transfer efficiency more rapidly over time than steel dowels, okay? And here's a graph. This came from Washington State. The purple lines are epoxy coated, the gray lines are FRP. The lighter colored lines of either color are the initial numbers, and the darker lines are the long-term colors 6 years later. And in all cases, you see a little bit of a drop-off, but the drop-off for the FRP bars is much more rapid than it is for the epoxy. Numerically, it looks like this. Load transfer statistics, 2012 average epoxy coated bars 67%, 6 years later dropped to 57%. FRP started at 51 and went down to 32. If we go down to the more preferred measure of relative deflections, the epoxy coated went from 1.68 mils relative deflection in 2012 to 3.05 in 2018. GFRP started at 2.69 and went up to 4.79. Now, I would say that I would note, yeah, it increased, but I would also note that 5 mils relative deflection is not a bad number. Despite the lower load transfer efficiencies, there's typically little difference in pavement performance between the two, which suggests that joint-related pavement performance is not entirely related to load transfer efficiency. Not a good metric, okay? Relative deflections were similar, like I said, still within accepted limits. We've already gone over this data, so I'm not going to hit it again. Other key conclusions: abrasion wear might be an issue. This comes from some studies done in Ohio back in the 80s. A group did a study of I-77 where they noted, quote, mechanical degradation or wear of 1-inch diameter dowels was sufficient to reduce the cross-sectional area by as much as 1/3. I find that shocking. So I'm not sure why that was, and it would be interesting to go back and look. No one other studies have noted abrasion wear for FRP dowels, but maybe we ought to pull a few out and take a look. Regardless, I think having a test protocol and limits on abrasion, that should be done. We need to establish some limits. The test protocol is out there, and even without the limits, we can certainly tell, A's got better abrasion characteristics than B does, and I think that's worth doing. Also, it's worth noting that if you build pavements on stiff foundations, cement-treated bases, lean concrete bases, asphalt-treated bases, less load goes through the bars. All your deflections are lower. So joint width and foundation support have big effects on load transfer and relative deflection for any dowel system, but especially for FRP dowels because they've got that low shear modulus. And this is a recently constructed pavement in California. It's about 4 years old, I believe. And in their study, they found that the relative deflection of FRP dowels on a lean concrete base was less than 1.5 mils, practically nothing, okay? So again, we got to look at these pavements as a system. It's not just the dowel bar we're looking at. We're looking at the dowel bar, we're looking at the foundation, we're looking at the slab thickness together. All these things influence the behavior of the dowel bars, okay? In our talking to the contractors and the agencies, our interviews, here's what they had to say. In general, they liked them. They said FRP bars generally work well. They've noted no pavement performance problems. Contractors love the lightweight for the reasons I told you about, possibility of better field production, fewer lifting injuries. Some folks even mentioned sustainability, less fuel consumed in transporting and moving the dowel bars. No one that we interviewed noted any problems with dowels falling out of the baskets. And they did notice that the price on the FRP bars was becoming more cost competitive with steel dowels, maybe not so much because of the cost of the FRP, but because the cost of steel was going up. FRP was a little more stable in pricing, I guess you'd say. On the negative side, everyone's using bigger dowel bars for the most part. Increased dowel size makes them less cost competitive. And there were some supply issues with FRP noted in Quebec in particular. And everyone noted that there was a need for better guidance and better specifications. They want to use them, but they don't know how to use them. And that was the reason for this research that was done here and this publication that ACI next is going to put out. There were some concerns noted with the use of plastic modular baskets when you need to use those. One was the time and labor required in the field for assembling the baskets. One contractor noted that the baskets seemed flimsy. Didn't say they had a problem necessarily, but they questioned whether they were structurally adequate. And I would say that is an issue. We don't have any design standards for baskets, whether they're steel or FRP or anything else. We don't know what the design criteria are, deflection or loads or what else. That's a question. What do we do with baskets? Then there was some difficulty anchoring some baskets without damaging the basket assembly. You whack on plastic real hard, putting a nail through the foot of it, and you might break the foot off. At least one agency expressed some concern with what happens in the long term, recyclability of FRP. There's no standard process, no upscale availability of FRP recyclability for dowel bars and rebar at this time. I suspect something will come in the long term, but there's nothing out there right now. So conclusions and recommendations. Research and experience do support the use of FRP bars in highway pavements. There are issues or concerns with load transfer efficiency and relative deflection with FRP dowels, but long-term performance says it's not mattering in terms of the performance of the pavement. We do have some guidance out there, as I mentioned, the ASTM new specification for the materials, and ACPA T253, M250, it should say T253, M254, that's a typo. The ACPA specs anyway, with both the testing and the material specs. And there is design guidance presented in the report that we produced for this presentation here, both conservative guidance and more aggressive guidance. They are non-corroding, they are lightweight, but basket installations are preferred. Here's an image of the draft report. My understanding is that the real report will be coming out of ACI any day now. They're working it through the system there. And I'd like to acknowledge ACI for their funding of this effort, and Dr. Taylor and the National Concrete Pavement Technology Center at Iowa State University for bringing me on to work on this. And then these are all the folks that were participants in the interview process of the agencies and the manufacturers and contractors along the way. These folks all contributed substantially to the report itself, as well as to the content of this presentation. So with that, I think it's time to open it up to questions.
Thank you, Mark, so much. Great presentation, great work. You comprised all the information you had in one presentation, so that was wonderful. So let's move to our question answer session. We have a couple of questions. Our first question is, it's on slide number 39, how to calculate the bearing stress now, because I think it might be something outdated or it was early in the years. So is there any guidance provided on the design of FRP dowels specifically?
I'm not sure where the question is there. Let me try to address a couple things. The bearing stress equation that's based purely on mechanics. So yes, it was developed for use with metal products, but the theoretical part of it still applies. So it would apply no matter what the equation doesn't know if you're using steel or FRP. So if you plug in the appropriate stiffness of the material and so forth, you should get a proper estimate of the bearing stress there. What was the second part of it? The very last thing. There's something about design. Yeah, it's something about designs. We don't really, again, we don't design for bearing stress. We can calculate the bearing stress, and we can calculate it with this equation. We can calculate it using finite element analyses. You can use, gosh, what's the name of the program that escapes me right now? Abacus. Abacus is one that we've used for looking at these things, and you can calculate using Abacus as well, and they'll give you reasonably consistent numbers. But again, if you're going to design, that means you have to have a limit, and we don't know what the limit is or should be necessarily. And perhaps the questioner is going back to the comment I made about the fact that the bearing stresses tend to be higher for FRP than for steel, based on information and testing done by Max Porter at Iowa State University. But there's nothing that's come out of that into a design procedure really. So.
Okay, I think that answers the question.
I hope.
Our next question.
If not, contact me by phone or email afterwards independently if you'd like, and we can talk. So.
Our next question is, so can we use FRP dowel bars in the existing structure, and where we can find more on the design details if we want to use it?
Can we use FRP dowels in existing structures? And by that, I would assume you mean as a dowel bar retrofit, perhaps?
Yeah.
And I would say yes. If you can use in new construction, you can certainly use in dowel bar retrofit as well, and you would follow the same guidance that's presented here. You have guidance for using steel bars in those situations, and I guess a lot of times we increase the size of the diameter of the bars for steel when we go to dowel bar retrofit. Sometimes I would use proportionally the same size. If you're matching behaviors, you'd use proportionally larger bars for the FRP as well, I suppose. Although again, experience is indicating you probably use the same size bar.
Yeah, so I think that's a good answer. I have another question which says, are freeze-thaw cycle a factor accentuating abrasion?
Could you read that? Are freeze-thaw cycles a factor in what?
Accentuating abrasion.
Accentuating abrasion? They should not be with the vinyl ester and If you're asking if freeze-thaw cycling of the bar itself is going to affect its resistance to abrasion, not to my knowledge. The answer is not to my knowledge. I would not think that that would affect it.
One other way to think about it perhaps is that as temperatures cycle, you're getting horizontal movement in the slabs. Could that be the source of abrasion?
Oh, absolutely, yes. I mean that is a source. Yeah, daily and seasonal cyclic movements of the bars would be the source of the abrasion. Yes, if that was the question. Yeah.
Okay.
Thank you, Peter.
So, is there a market availability of FRP dowels all over the country, or is it minimized to specific regions of the country, or it is limited to specific regions of the country? Okay.
I don't know of anything regional that would limit the marketability of FRP dowels if they are useful. If they are a useful alternative to conventional steel, there's no environmental factor or geographical factor or temperature factor that I'm aware of that would limit their use. If you find them acceptable from a structural standpoint, they should be acceptable anywhere.
Yeah. So you also talked about the GPR system. So we have, it's not a question, but it's a concern, or maybe you want to add something to it. GPR and ultrasonics are unable to locate GFRP bars because the properties they focus on are nearly the same between concrete and GFRP. GPR may be able to see it occasionally, but it is not guaranteed.
Well, my impression was that they were, I mean, there are limits on using GPR, obviously, with the moisture content of the concrete at early ages. But my understanding is that GPR and ultrasonics will see them. It may be, the densities, like you said, the densities are fairly similar, but you do have a distinct, with ground penetrating radar, you have a distinct boundary there where you're going to reflect the radar between the concrete and the FRP. So I guess I'd need to talk to this person more and see what they. I've not seen anything that says that it's possible, but what I've read has not been along those lines. It has been that you can use them successfully. So I guess we'd have to compare notes and see what the person is referencing.
Yeah, I would definitely ask them to contact you. But I agree with you, Mark, because we had a webinar last month, which was, and the person, he was subject matter expert on GPR for GFRP bars. So I agree with you. I haven't heard that it goes wrong, but yeah.
Perhaps it requires a higher skill in identifying the parabolas in the plotting that you get, but it may be that you need a little more expertise to find things. But my understanding is it's quite doable. But
I agree. Yeah. So with this, we end our question answer session. Thank you so much, Mark, again, to answer all our questions and for the outstanding presentation. So before we go, we end our session. A few exciting announcements before we log off. Here on the screen. So Next has released request for proposal for 2025 fundings, and we have total of 17 requests for proposals, which includes 6 in research and development category, the 10 are in standard and guidelines, and 1 in professional development. Anyone who is interested, please submit your proposal. Our deadline is early October, so and we have provided all the information on our website, that is www.nonmetallic.org. If you go to request for proposals, you will find all the details. If you have any question, you can always reach out to us. And this is like our webinar list, the upcoming webinar list, which you can register at ACI University. Also, Next has a full day virtual webinar next month, that is on September 24th. The topic is structural rehabilitation and strengthening using FRP composites. We have several speakers, so do register for it. And with this, we end our today's session. Thank you so much for attending this webinar, and we will see you next time. Thank you. Thank you, Mark.
Thank you all.
Bye-bye.